Greetings, I'm Humphrey from Carnegie Mellon. Today, I'm here to present Freeform Fabrication of Fluidic Edible Materials. Food is beyond nutrition. In HCI, we are interested in using them to mediate sensory experiences and to influence user behaviors, to display information, and to leverage them as shape-changing interfaces with novel augmented functions. However, if we look at the design space of digital food fabrication, we will find that while a wide range of materials and shapes has already been navigated, printing fluidic materials into 3D shapes is still challenging, and we are dedicated to enable this design space. In particular, this design space is challenging because fluidic materials cannot retain their shapes well after printing, which also makes it difficult to create complex structures. So, in response, we propose to adapt embedded printing for foods. Embedded printing was originally used in biomedical engineering. Instead of printing onto a platform, this method extrudes materials into a gel-like bath, which functions as an omnidirectional support during the printing process. In this work, two support bath formulations are adapted for food printing. The fabrication method consists of 3 steps: support bath preparation, materials embedding, and print release. Since the 2 bath types each has their physical limitations, we provide guidelines for choosing the appropriate support bath formulation based on the embedded materials properties, as well as a computational toolkit for generating freeform print files. Finally, we use these tools to explore the enabled design spaces, including artistic and functional ones. We use a hobbyist desktop 3D printer in this work, which is outfitted with a syringe pump and a blunt tip needle to poke into the baths. The printer takes conventional G-code files as input, and it can create 3D objects with non-planar toolpaths. When creating freeform shapes, we found that where conventional printing methods fail to create a gentle overhanging slope, embedded printing can keep going without failure and produce an almost horizontal overhang. The advantage of using embedded printing is even more visible when we print highly fluidic materials, like a wet dough. In this experiment, we can see that compared to a conventional printing method, embedded printing can accommodate a high water content dough without visible defects, and after printing, the dough can be heat cured to set its shape and retrieve from the bath. In terms of the printed shapes, we also developed a toolkit for generating 3D toolpaths. In addition to the conventional layer-by-layer slicing and constant extrusion profile, we also implement new functions like a freeform slicer to generate non-planar toolpaths, and a geodesic slicer to create surface patches with an uniform line spacing. Users can also assign toolpaths with a varying thickness to create more expressive shapes. To exemplify the print file generation workflow, given an X shape like this, and a helical slicing surface, we can use the freeform slicer to create a non-planar toolpath with an increasing line spacing toward the top. And the toolpath can be assigned with a decreasing thickness to make the two halves even more aesthetically contrasting. Once that's done, a compiler takes over the results to produce a corresponding G-code file, which can be directly used by the printers. With these design tools, we created several confectionery arts to demonstrate the enabled design space. Using the sacrificial support bath, we were able to print chocolate into delicate 3D shapes that are otherwise difficult to print with existing techniques. It also augments unskilled users to create desserts that would traditionally require fine craftsmanship, like jelly arts or wagashi. The bath can also be used as a timed release mechanism. After printing and trapping the shape in the support bath, the shape can be controlled released by exposing the block to a dissolving vector, like using heat on a gelatin block. For instance, a jellyfish printed and trapped inside of a gelatin block was set free in a bowl of hot water. In this video, we can see the bath melting away and the jellyfish becoming adrift. We speculate that a design like this can be used for signaling the cooking process. Also, taking inspiration from fried dough, we explored the shape-changing dimension of embedded food printing. A wet dough was printed and cured into a 3D shape inside of a sacrificial bath, and after taking it out and drying it, the object was puffed in hot oil to increase its size, enabling a 3D fried food design space. Looking forward into the future, we believe that for shapes makers and researchers using the embedded food printing method, we'll be able to create computational cuisines that are personalized, functionalized, and enable interactions, such as using food as holographic displays. This image shows a jelly block embedded with hollow channels. When perfused with dyed fluids, the jelly works as a segmented display to show the digit 1 and 0. But still, there are even more exciting design opportunities to explore in the future. This is the end of our presentation, and we are happy to take questions. Thank you.